Howdy everybody, Dante here, and today we're going to be talking about pointers because with the recent programming assignment 2 on doubly linked lists, it has become abundantly clear that there is a lot of misunderstanding gap with pointers and the way that they work. So I'm going to go through this slide deck here as quickly as possible and we'll discuss pointers. So what is a pointer? A pointer is basically an unsigned integer which represents a memory address. So this object star is creating a pointer which stores a positive integer and unsigned integer, and it's referring to this object which lives somewhere in RAM. And the location of that object in the RAM, which is addressable, is stored in this pointer variable, which is on the stack. So if I create a regular object on the stack here called stack object, I can create a pointer to that stack object by using the address of operator, which we can see there. That creates a stack pointer. I could also create a heap pointer using the new operator, which you've seen before, I hope. So the important thing to note here is that pointers do not always refer to heap data. The first one refers to data on the stack. So what are the stack and heap that we're talking about? They're basically regions of RAM whenever the program's running. So this box over here on the right is basically like your program's memory whenever it's running. So at the beginning of the memory, at the very bottom, you have the static variables and program instructions, which are generally fairly small, as well as global variables, which are also hopefully small for the programs that you're writing. Then you have heap, which is a relatively large section that can grow, as well as stack above it, which they label here as local variables, which can also grow. Every time you call a function, you're adding stuff to the stack, and every time you return, you're taking stuff away. Whereas with the heap, you add stuff whenever you do new, and you take it away whenever you do delete. When I say that new goes to the heap and creates new memory, I mean it works a bit like this. If I invoke new and I say I want a new object, what happens is my computer goes to the heap section of memory and it finds a block big enough to fit the object that I want in memory continuously. Once it finds this block, it generates a memory address to the start of this block. So say the block starts on 0x987. The pointer that I will receive is going to be 0x987. So this is an instance of what happens whenever I do new. Whenever I do delete, for instance, if I said delete p, what happens is I give it a pointer to a bit of memory, and what it does is it goes out to that memory and it marks the object as ready to be deleted. So it's like there's a little field over here called del, and it marks it as ready for deletion, just like that. It doesn't actually really edit the object, at least not right away. And it doesn't edit p itself, like the pointer, the memory address that's there. So we could still use p to read to this object. But whenever I do subsequent new calls, it's very highly likely that this object will be overwritten by these subsequent new calls. And therefore, p will be pointing to an object that it does not own. This is what's known as a dangling pointer. If we invoke delete on an object that is not a pointer, p is a pointer, then what will happen is C++ will not compile the program because delete goes to the memory address where p is and marks it for deletion. Remember, delete did the little check mark here, whereas new created the continuous object and returned it to us. That's a brief description visually of what happens whenever we do new and delete. All right, back to the PowerPoint. Okay. So the stack's more organized and is faster, and the heap's more flexible because it can store larger objects. So a lot of you have been probably thinking, hold on a second, I've done stacks before. A stack and the stack are completely different, okay? A stack is a data structure. You've worked with it before. The stack is a section of memory, okay? Now, the stack behaves in a lot of ways a lot like a stack, but it's not like you can create another the stack without creating another program. The stack is also called the call stack. Similarly, heaps are a data structure. You're going to implement heaps later on in the course, but if you used a heap to implement the heap, it would be not great. Generally, the heap is implemented using a free list, which may end up being very similar to a heap, but depends on the implementation. You may implement your own heap allocator in CSCE 313, probably with a free list, and that depends on your professor. Okay, so let's get back to pointers. Stack memory is always cleaning itself up automatically, so you do not use new and you do not use delete. Heap memory's got to be managed by the programmer, so you create heap memory with the invocation of new, and the memory is freed by delete. So let's talk about some common problems. If memory is not freed, you get a memory leak, which generally leads to a slow and painful crash as the computer runs out of memory and it gets slower and slower and slower, and then it crashes hard. If memory is freed twice, you can, on Linux, get a SIG abort, which basically is an abort signal basically saying, hey, well, hold on, we did something illegal, we double freed, and it crashes the program abruptly. It'll also crash abruptly on macOS. It just doesn't have this SIG abort, the abort signal. It'll be the macOS equivalent, which should be super similar. If memory is accessed illegally, you get a segmentation fault, which on Linux, again, is a SIG-SEG-V. I believe I've seen on Mac before it being bad access for error bad access. They're both segmentation faults, and they both lead to pretty abrupt crashes. Okay, so let's talk briefly about the brackets operator. If you use new with the brackets operator, you have to use delete with the brackets operator. What does that look like? Well, let's say I have object star heap buff is equal to new object brackets n. Now this is different than parentheses. If I use the brackets here, then I have to use the brackets when I delete. Otherwise, if I forget to, memory leak. Now, if I didn't use the brackets whenever I first created it with my new, I used parentheses instead, I cannot use them with my delete. If I do, that will often, but not necessarily always, lead to kind of the double free / segmentation fault type stuff. So bad crashes. Okay. Now let's discuss some of our accessors. Dot, which you're hopefully a little familiar with, arrow, which you might be somewhat familiar with, and brackets, which you're hopefully familiar with. So, okay, we want to get access to data inside of objects. There's 3 ways to do it depending on the situation. Let's say we create an object on the stack here called stack, or we create an object reference, a reference to an object called stackRef, and point it at stack. We can access the object field by using dot object. So dot applies to objects and to references to objects. So objects, references to objects, we use the dot. Doesn't matter if the objects are on the stack or on the heap, all references will do a dot. And all objects have to live on the stack. You can't directly have access to an object on the heap. You have to have a reference to an object on the heap or a pointer to it. Okay. Pointers, like for instance, a pointer to the stack object or a pointer to this heap object, you always use the arrow. Okay, so use the arrow for every time you have a pointer. You want to access something. It works pretty much the same as the dot. And now finally the brackets, which seem a little unrelated. Let's say we have a buffer of n objects on the stack, or we do the same thing on the heap. To access things, we use the brackets, and then we would use a dot if the objects stored inside of it are objects. Now, in this case, it says object star, but the star is referring to the fact that this is a pointer to a collection of continuous objects. Therefore, the objects within are actual objects, so it's dot. Okay. Indirection, the asterisk. So let's say we have a pointer and we want to access the data in it. We can dereference it. That's a word you hopefully will hear a lot using the indirection operator. So if I have an object pointer called heap pointer, which is this new object, if I want to get access to a reference of it, I can dereference the pointer using the indirection operator. And now I have access to this heap reference. So heap reference and heap pointer both refer to the same object. You need to understand this if you want to understand the next slide. So pause the video, go back a bit, look at this, maybe Google a few things about it, because we're moving on. Equivalence between these different things. So let's say I have an object called A, which is a pointer, and it's allocated on the heap. If I want to do A arrow object, how does this break down? Well, this is the same thing as doing indirection of A and then taking the result of that and doing a dot. Indirection of A, remember, returns a reference to A. So then we do a dot on that reference. So that's why this is the same thing as this. Okay, now the brackets, they actually can be broken down as well. So with the brackets, we could do B bracket 3 dot object. This is the same thing as doing B plus 3 arrow object. B is a pointer. So if we add 3 to it, it adds 3 elements through our array and it gives us back a pointer. We can use the arrow because we're trying to access something within a pointer to get to the object. We could also instead manually indirect that pointer, dereference it, and then access the object via dot. So these statements are all equivalent to one another. At least these bottom three are, and these first two are equivalent to each other. So you can replace the arrow and the reaccess with dot if you're like uncomfortable with them. Please use the arrow and use the brackets. They are really good. But if for whatever reason you aren't allowed to because Dr. Lake says that you can't or whatever, use dot in those cases. Here's how you equivalently do it. So here's how we can find segmentation faults in our code. As I mentioned earlier, that's due to illegal memory access. You're going to want to use GDB if you're on Ubuntu or any other Linux, and you're going to want to use LLDB if you're on Mac OS or OS X, whatever it's called. So whenever you compile your code with G++, or if you're on Mac OS, you may use Clang++, you want to compile with this -G flag. This says to include debugging symbols. This means that the variable names, line numbers, and stuff like that are preserved, so it can tell you where and exactly why your seg fault happened. So -G, as it says here, compiles with debugging enabled so that they can understand your code. You got to launch GDB or LLDB by saying GDB and then the name of the program. So in this case, the name of the program would be a.out, so it'd be GDB a.out. If we did -O main, it'd be GDB main. If we did -O test, GDB test. Or we could do equivalently the same thing with LLDB main test a.out, whatever. Then you run the code inside of GDB or LLDB once it comes up after you run that command by typing R or typing run and clicking enter. The code will run, and then whenever it gets to a segmentation fault, it'll say, error, and you can then type BT, which stands for backtrace, or you can spell it out. And that'll tell you exactly where your segmentation fault happened. If it's not being very detailed, even in the backtrace, like on line numbers and things like that, that means you may have forgotten to do the -G. So you might want to go and quit out of GDB by typing Q, or LLDB by typing Q, and recompile again with the -G enabled and get to that point again. Okay, finding memory leaks. So on Linux, there's a tool called Valgrind. You compile as if you're doing like GDB. And it can run, and it's pretty comprehensive and pretty good. But a solution that works on OS X and all other platforms is the address sanitizer. So you compile your code in the following way. G++ fsanitize equals address. You can also do a -G if you want. That could help, but this is the most important part. This puts the address sanitizer on there. So now whenever you run the program, it runs with address sanitizer, and it can help with finding leaks. It's not perfect. It can sometimes miss things, and it sometimes isn't great with doing output, but you can configure the address sanitizer in multiple different ways. This is just the basic configuration. I encourage you to look up more about it if you are going to be using it a lot. You're going to need to understand, though, all of the different ideas mentioned in this, how pointers work, how new and delete work, all of this kind of stuff. And also, you should not run address sanitizer programs in GDB or LLDB. It's not going to work. So if we go back a bit, we're going to want to discuss a few things here. So when it comes to the difference between references and pointers, pointers can be null. Pointers are also mathematical objects. They're integers that can be manipulated. References are a lot like pointers, but they cannot be manipulated and they cannot be null. They basically directly refer to the object. A few other things to note about pointers and references is every time you use a new, you're going to have to delete eventually. You have to make sure, though, that you're the one in charge of deleting it. For instance, let's say that I have a list, like a linked list, and I'm trying to iterate over the linked list and print out items in the list. In doing so, I'm going to create a pointer called cursor or iterator or something of the sort and use this to iterate over the list. However, that pointer is not going to allocate any new memory. I'm not going to say new. It's basically a stack pointer referring to these heap objects. And the objects themselves do not need to be deleted during the printing. They only will be deleted later when the object is no longer needed for anything. So I do not want to use delete anywhere within this function. That was a pretty common misconception that we ended up seeing a lot during the programming assignment. Hopefully, again, this has cleared up a few things about pointers and also about the differences between stack versus heap and arrow versus dot. Let me know if you have any questions. Awesome. Thank you so much for watching. Goodbye.